So this is joint work with Jeremy Youngquist and William Sims. I won't really get to some of the stuff that William has done. I forgot to mention Ming Yu, who was also a co-author in a previous talk that I gave in the previous workshop, and Jörg Peters, who is a colleague. So these are, Jeremy is commonly advised by Jörg and me, and primarily was supported by DARPA during the time 2017 to 2020. A small part of the work is also was supported by NSF FRG, where some of the rigidity community people, including Bob Conley and Shlomo Gottler and Louis Theran, and not Louis, but Miranda, were co-PIs. Okay, so I just wanted to start with where we started, right? And why we got interested in this. So essentially, in the current state of the art, when this, 3D printing and microstructure design and all that is almost de rigueur right now. And the way they design and analyze and model and all that is sort of built up historically over long periods of time, over techniques and tools that people developed. So essentially, there is an underlying microstructure in nature. I'm using the word micro not to mean micro scale in the sense of micron, but it could be nanoscale or whatever. So it could, you have some statistical, mechanical, it could be atoms, or it could be at the level of particles or whatever. You have a statistical mechanical model. And that is essentially already, particulate, there are small discrete interactions which are then averaged out statistically. And then you have, you could also have at a level where you're partially designing a composite material, such as foams. Sometimes you have materials that are grown in vats. This is called this thing that I'm pointing to here. Can you see my pointer, by the way?
I can't. Can you move it around in case I'm missing it?
Yeah.
Oh, yes, I can. Yes, I can.
Yeah. So okay. This thing up here is something called PICA, which is a carbon fiber composite, which is supposedly some kind of magic material that they use because of its ability to withstand heat as a heat shield for space re-entry vehicles. NASA has sort of developed this thing. If I get a chance, I'll show you at some point an animation they have on how heat acts on it. And of course, there are jammed spheres, which I've seen several sort of talks about it in this workshop as Mini-symposium. So so you have these partially designed, I would say, composite materials, including things that are supposed to mimic things like bone, which are grown in vats, like foams and so forth. This is a type of a foam. And the way they are represented in order to continue to model and analyze them is in a discrete way. So essentially, you have, these are Apollonian circle packings. These are the corresponding sphere things. You can have what they call skeletonization. They have a graph type structure where they do some sort of approximate analysis of load. So they have some kind of a discrete representation of that thing. And then they continue and produce what is called a homogenized bulk or effective properties. I use this crazy word multiphysics, which is also used a lot for good reason, because when you think of physical properties, for example, if you think of stress, the stress could be mechanical stress, or it could be electrostatic stress, or it could be magnetostatic stress, and the mathematical structure of the equation and how you would analyze it is almost exactly the same. Stress is stress. And so even though you could be talking about physical stress, you can use the same equations in a way to talk about electrostatic stress. So when I say multiphysics, I mean a lot of these sort of the underlying mathematics, cryptomorphic physical properties that look the same and can be modeled the same way. So they then what they do is they take this discrete thing, and then, which could be somewhat randomized, could be stochastic, it could have multi-scales in it, multiple scales, and they have well-developed techniques to derive sort of bulk properties of these things. And it's based on something called a representative volume element. So there's a lot of techniques for doing that. There's an entire book you can search on Google, several books on how do you derive representative volume elements for these types of composite things. Concrete, for example, concrete looks like this. And then what they do is, once you have this representative volume element and sort of a homogenized bulk representation, you then have a continuum mechanics formulation of your physical property. So now you have, you started out with some kind of a discrete or particulate structure, and you converted it into some kind of a continuum mechanics formulation of the same properties that use physical properties. So the properties originally may have been in the form of constraints or sort of conservation laws concerning energies conserved, momentum is conserved, or whatever, if you have particles that are moving around. But then eventually you come up with this bulk property. And so that's what I've represented here. You have particulate, you sort of have a network type model, you do something, you have a random microstructure, you do RVE type of thing, and you sort of represent it as some kind of continuum. Then you sort of almost do the reverse process one more time. I mean, this is just historically the way things have developed. So now that you have the ability to make very fine things, print really tiny microstructures and design them to enormous precision, what you do is you design your microstructure and the shape together. So it's a common process, which is now, again, lots of software tools and so forth, called topology optimization. So what it has is an external sort of boundary constraint, both on shape and loading, whatever. Again, I'm using loading in a very general way, as though it's mass and force, but it could be electrostatic properties, magnetostatic properties, and you could even go into dynamical properties. So I won't go too much into that, so I won't emphasize that. So so you have this guy sitting, and you have certain loads and certain overall structure, and you want to optimize, let's say, the weight, right? You want to be able to take the load and satisfy the boundary constraints, but at the same time, reduce the weight, for example. So you go through this process, which they call topology optimization, and it goes all the way even inside to designing a type of a microstructure, which you can barely see. You can, at the moment, they can even print things where the members are as small as 10 microns or even smaller. They've even gone into the nanometer scale. So they can actually print these things. So then you sort of decide, okay, this place is going to be this microstructure, this place is going to be this microstructure, and so forth. And then you have some humongous thing like this. Now they can even print an entire bridge. Yes, you've probably seen this 3D printed bridge in Amsterdam. So, and now there's one in Shanghai, which is even bigger. And it's been designed down to the microstructure scale. So how do they do that? So to do that, again, they discretize, right? So what they have is, so this is from a book, on topology optimization. There's some bridge, there's loading. It has some representative volume element, because this material is made of something, and that something is some discrete thing, concrete or whatever. So it has a representative volume element, which, already bulk properties and continuum has been, the continuum bulk properties have been used to write the PDE down of whatever it is you're trying to optimize. And then you make finite elements, you find a kind of a different type of discretization that helps you solve the finite, that helps you solve the PDE. Often it's not just solving a PDE, what you have is a PDE constrained problem. If I get time, I'll talk about it. We did some for electrostatics. So you have a PDE constraint problem on the finite element space, and then you use that to figure out, to do this step of figuring out what microstructure has to be, what the overall, the smaller shape has to be that satisfies the boundary constraints and optimizes weight, So it's a PDE constrained optimization problem. To solve that, you rediscretize and you do this, right? So you have, you're starting from something discrete, you're making it continuum, and then you're going back in order to optimize something, you're going back, rediscretizing in a different way, right? And then when you're done with it, you have to now square the microstructure that you have designed, that you want to print, for example, with the underlying material microstructure, and or even between different microstructures that you have for different pieces of this fork. There's a common example they give for topology optimization. You have to, one place looks like this, another place looks like this. You have to connect them together, right? So there's this whole post-processing where just to ensure connectivity. It's a good reason why they don't add connectivity as part of their constraints when they're solving, because connectivity is a nonlinear constraint. So it's okay to solve a nonlinear optimization problem, but you want linear constraint. You don't add nonlinear constraint. So they do this post-processing of both getting their own microstructures that they have designed for different pieces of this object to talk to each other, to be even connected, and also to make it consistent with the underlying microstructure. Sometimes the underlying material microstructure, which could be composite or something like that, or just natural. Okay, so whoops, I don't know why that slide looked like that. That was weird. Let me see. If you give me a second, I'm just gonna get rid of this thing on top. Yeah, somehow that slide was messed up. This shouldn't even be here. Okay. Okay, let's go back. Okay, so the goal is to somehow cut out somehow the control of my, yeah, there we go. The goal is to sort of cut out all of these intermediate steps, B, C, D, E, F. You may not remember B, C, D, E, F, but let me quickly go through this. We start out with the discrete representation of some underlying microstructure. Then you did a homogenization to get bulk properties. You did you did a design. I mean, you added on your PDE constraint optimization problem for shape, weight, whatever, and with boundary constraints and macro shape. And then you designed this whole object with the microstructure. And then you did that by rediscretizing, made it finite elements and did everything. And then finally go back to your discrete microstructured world and do some post-processing to make things are consistent with each other. And the idea is to just sort of get rid of all that. Okay, so this is the big ambitious goal. You have a discrete initial representation. You choose it nicely so that it's scale invariant, which means you can use the same representation for various things. It is flexible in the sense, as I said, all the cryptomorphic physical properties, one type of stress or another type of stress, whatever, it can deal with all of them, essentially using the same representation for everything. It allows hierarchical building because that's important, that for this multi-scale, natural multi-scale structure that materials and others have. And then you want to, have certain built-in properties, if possible, for your canonical canonical discrete representation, which you don't have to later on do post-processing to connect things up or make sure that they are rigid, not just connectivity, and go beyond that, say, to say, let's say I want to ensure minimal rigidity so that the thing doesn't fall down. After I've designed all this based on shape, I don't have to connect things up so that it at least stands up, So to avoid post-processing. So you want inbuilt certain properties. And of course, obviously you would like it to be flexible in the sense that obviously there's all these tools for continuum mechanics. There are all these tools for, finite element computations, for representative volume elements, for homogenizing random microstructure, all this stuff. So you wanted some kind of interoperability so that, if you did have it in your representation and you wanted to compute, let's say, homogenized bulk properties from your representation and then send it on to some PDE solver or something with a finite element solver, you should be able to do it, right? On the other hand, if you don't want to do that and you want to compute the PDEs directly using your own representation instead of computing using finite elements, using homogenization and finite elements, you should also be able to do it in some using the discrete representation itself. So that was the sort of ambitious goal that we started out with. So of course, we go back always to the expertise that we have. And it seemed that geometric constraints had already been used. I mean, first of all, there's a variety of them that you can, many of them can be dealt with in the same way or similar ways, or at least the theory, there's an underlying uniformity to the theory that you can try to use. So here's some examples. And we had already used, geometric constraints to together with the techniques, underlying techniques that they give you to model various things. I mean, I've been doing this for a couple of decades, so been used it for all kinds of different things. Okay, the techniques were the specific techniques: combinatorial rigidity, configuration spaces, some symmetry analysis, and some recursive decomposition, and the idea of emerging rigidity. All of these we have used in various ways. So the idea was to take advantage of all of that. So the sort of common representation we decided that would be most useful to that for various reasons. I'll tell you some more as to why we picked this particular representation as sort of like the underlying thing that that we could use. First of all, it's, we wanted succinctness, which means it's, efficient to represent and so forth, and very small, in other words, space saving. And it should be rich in the sense you can get irregular microstructures, you can, have some kind of a standard way by which you can generate irregularities, you can analyze, if you wanted to get a homogenized or representative volume element for there is a random process that generates the irregularities, so that you can use that random process, kind of a martingale or something, to actually figure out what the homogenized property is. We wanted it to be versatile, which means that it can represent all the different multiphysics properties. You can use it to represent potentially multiple types of constraint systems, and multiple physics properties on each type of constraint system. And then, as I said, I wanted interoperable and so on and so forth with existing software and so forth. And the key thing is that we wanted it to have sort of built-in minimal rigidity, not just connectivity, but actually one step further, minimal rigidity, so that we can don't have to do the post-processing in the end. Okay, I'll tell you a little more as to where a lot of these ideas came from. Okay, so and of course we wanted to, we wanted the representation, whatever that underlying representation is, should be good in the sense that we can take, we can use that representation as sort of like the underlying vocabulary and do all the normal things that people do when they design shapes. So they decompose it into pieces, and then they fill each of the pieces with some microstructure, and then they try to connect them together, and the connection we should be able to do it while preserving all these built-in properties, all of the, and then we should be able to do the usual things that the people do to optimize the shape outside. We should be able to do the usual things people do if they wanted to compute PDEs on it. So in other words, attach, you have a discrete underlying representation, but you should be able to attach some kind of splines or continuous representation on top of it if you wanted to do some PDE solving. So, we wanted that, all of these. And another important thing, which was actually one of the challenge problems that the DARPA gave us, was, especially if you design irregular microstructure for printing, which is now the thing. So you actually print out something where you intentionally add irregularities, because those irregularities stochastically give you better properties. And that was what was found using that carbon fiber that I showed you in the beginning. So then you need to be able to print it. And then this is this humongous thing. You might have like 1 meter cube of tiny, the microstructure maybe of the type of 1 micron, and then, or 10 microns, let's say. And then, so you have this huge thing, which is irregular, and it's not periodic, and you want to be able to print it. So printing is typically still done by slices. So there's, how the slice is processed is changing. Typically, the slice used to be processed by one sort of nozzle following a path along that slice. But maybe you don't, nowadays they have multiple nozzles, but still a constant number of nozzles depositing the material, or there are others which sort of burn, melt the material, but still it's melted in particular places. So at best, an entire slice may be printable at the same time, but it's still done in slices. Okay, so you have this, irregular microstructure, and you want to be able to cut slices through it, and which is a humongous thing. You want to be able to store. You can't possibly store all the information in a slice. It has to be generated somehow as you proceed. So it has to be some kind of a generative model. Okay, so so we chose this corner sharing tetrahedra as the sort of underlying vocabulary, and oops, my goodness, I wonder why I lose control when I get into this present mode. Let me see. Okay, so corner sharing tetrahedra, so they are underlying every one of the pictures shown here. So one abstract representation with many interpretations. So we can, there's corner sharing tetrahedra that are underlying this thing of jammed spheres, these packed fibers, and we have attached some splines on top to show this implicit splines to get this curved structure on top. And this you can probably see, just made these tubes attached now. Okay, so so the idea is that the cost edges can represent bars, or they can represent incidents of sliding fiber segments. They can represent touching particles if you're depositing powder. And depending on physical properties assigned to the edges and nodes, they can model mechanical or electrodynamical stresses. So the rigidity, stiffness, Laplacian matrices, all of these have meanings in all of these different physical or multi-physical senses. Okay, so the commonest notion of what is this, this corner sharing tetrahedra is something called the kagome, and it's found in nature, in zeolites, in multiple types of crystals, cristobalite, and I think quartz is like that. So it's actually found in many silica-based, because silicon dioxide has this kind of a structure. So essentially they all come from nature in a way. And I'll show you in a couple of slides that we can, we can, yeah, I think there's nothing more to show. This is just, I'm showing the rigidity matrix here. And just to say that, you can compute stresses, and this was just a simple stress computation of a load on this object, which was an original something like this with a map, with a continuous map that curved the whole thing. And it didn't curve curve the whole domain. So in other words, the points went into an image, which is image domain, which is curved, but on the other hand, that they are connected by straight bars. And then we just did this, sorry, the points are connected by straight bars. And then we just did this very simple stress computation to show you where the compressive and the greens are the greens, and the greens are the tensile, and the reds are the compressive stresses. Just shows the signs. Okay, so the reason we chose corner-sharing tetrahedra, we did a literature search on the physical properties of these types of three-dimensional Kagame. And the people had, and of course we were not the first, there have been since the 2000 a huge amount of study on these unique suitability of these Kagames for mechanical, acoustic, thermal, magnetic, electrostatic, photonic properties. Okay, whatever, you name it. It's been a favorite by a lot of people. So these are all links. I'm not going to go into the links there. Hopefully I'll provide the slides to Christoph, and you can go and do this. They've used it for everything known to, and there's this sentence that basically we found in one of the papers, which really seemed like they think of it as magic. Okay, so it says that best truss type lattice structures. One of the first people who studied this was a guy called Hutchinson, who was at Cambridge, and I think he's written some papers with Simon Guest, with some of the combinatorial rigidity people here will know. So essentially, they have actually experimentally tested, what they call this double layer Kagame, and wire woven Kagame and things like this for all of these different types of properties, right? So resistance to plastic buckling, it's in the elastic regime, the plastic regime, heat transfer characteristics, thermomechanical properties, thermofluidic properties. So they even actually think about this mesh of Kagame through which some fluid flows, right? So in other words, you're looking at the complement of the Kagame lattice where the fluid is flowing. Kagame structure through where the fluid is flowing. So they have studied it for everything, and they call, and they've this thing called the wire woven bulk Kagame isn't even written in this kind of microstructure literature. They just write it as WBK, and everybody understands it. So so we were definitely not the first people. It occurs in nature. It occurs. It has already been studied by mechanical engineers experimentally and so forth. So in other words, we felt like we were in good company in choosing this this particular structure. Okay. So, so this is the end result of some things that we did. And so this is where the rest of the story is going. This just shows a picture of an object that someone wanted to model. The standard classical way they do it is split it up into tetrahedra. So we have these tetrahedra, and then we fill the tetrahedra with microstructure. And of course, the microstructure that we choose are these corner sharing tetrahedra. Costs and the have this built-in rigidity properties. We can sew them together across these boundaries without using a simple technique and without losing these rigidity properties. What is not shown here is what we call boundary stiffening. If we don't sort of stiffen the boundary here, as you can see, if it's just all free here, the whole thing will just collapse. We're thinking of these costs as, in this picture at least, as in the pin jointed, so which in other words are usual bar joint structures, which doesn't change whether you have bars at the 6 edges of the tetrahedra or a solid tetrahedron. It's the same thing. So and you can refine and add irregularities and all this other fun stuff, and I'm going to get to that. Okay, so there's a paper that was written by, as I said, this is the reference that I mentioned, by Fleck and Hutchinson, who had done all kinds of things like this. So if you this is called you can see that this double layer Kagame, they call it, but in this case it's multiple layers. This was actually printed, and they loaded it, and they did all this experimental stuff. What we can show in this case, of course, it's not a pin joint, because it's it's just a material that's actually, it's not in the form of a joint, but the whole analysis was done as though it were a bar and joint structure. And they showed that for the same number, basically for the same amount of mass, it's stronger than what is sort of like the gold standard microstructure, which is called an octet truss. It's stronger than that. And what we are essentially thinking about is to ensure that those properties can be analyzed, sort of using rigidity techniques, and that these stress response can also be analyzed using discrete kind of rigidity techniques. Maybe not to the level of exactness that you might get from using finite elements, but quick, extremely fast approximate computation from which you can do the design, and then later on do more finer finite element computations. So one important, so essentially think of this Kagame as the basic vocabulary for a design space or cost. I don't want to use Kagame because it's basically corner sharing tetrahedra, and that's better because it just, the name explains what it is. We need to, so if you just think about these balls without actually stiffening the boundary of the balls, you can imagine if I hold them, they'll all fall apart, right? So we need one of the key operations in this, using this vocabulary, is the stiffening of the boundary. So that's where we use this rigidity, because it's we do use generic rigidity. Understanding that the condition number of the rigidity matrix and so forth will depend on how close it is to actually being a plane, for example. And the way in which we show, and because it's a very special structure, although we know 3D rigidity is a hard problem, for these special, because we're choosing corner sharing tetrahedra, we can actually show that we can prove rigidity. Okay, so the second operation, so the idea is to think of this corner sharing tetrahedra as a design space where multiple different design operations can be done, right? So the one operation that I showed you was stiffening. I just wanted to mention it up front because, when you have these boundaries sort of hanging out like this, the whole thing is definitely not minimally rigid, and that's one of the key implicit properties that we want to guarantee. So the stiffening is an important design operation. The second design operation that I'm writing about here is the addition of irregularities, right? So we're selling this as having a common representation that can represent naturally occurring microstructure, composite microstructure, printed microstructure, all of it, irregular microstructure, everything, and use different physical properties and so forth. So we need to have a standard way to generate irregularities and to be able to analyze the effect of those random microstructure, and, for example, do things like print it. So this we showed, some properties, proved some theorems to show that the space, you can actually explore the entire design space using these, flips. And the three-dimensional version of the flip here is shown. You can see that there is this two-dimensional Kagame here, a piece of a Kagame, two corner sharing triangles. And you can see if I filled it out as a quadrilateral here, these are the other two opposing ones. So essentially, you can think of the Kagame as being built out of, I think I had that in another, yeah. So you can sort of think about it as built up as layers in in 4 directions, one parallel to each direction of the tetrahedron. And each layer is a two-dimensional Kagame. So you have one set of parallel layers going this way, And for each one of these faces of these tetrahedra, you have another set of parallel layers. That's what this picture is supposed to show. And so essentially a lot of the analysis can be done these layer by layer in the 4 directions. So here I'm showing, in this layer, in this middle layer here, we're just doing what is, this is the original triangulation. Here's your corner sharing triangular structure obtained by this simple midpoint operation. And then you make a flip, the usual familiar flip that everyone knows, diagonal flip of the triangle. And that this is the corresponding structure. And that is shown in 2D. And that 2D thing has been performed here between here and here to get the 3D flip. Okay, so we can show that essentially the entire design space of corner sharing tetrahedra can be explored by using these flips. And we can create irregular structures. I mean, someone tells you create some holes here. We can do that using flips. There's a standard, an algorithmic way to do that. And, we can create, have a random process that generates things that look like that. I mean, it looks like concrete. And then, so because it's a random process, a stochastic process that generates this, we can then, analyze it using this standard techniques for representative volume elements. The randomization, the stochasticity is under control in a way. So we can understand the bulk properties of these things using a discrete method to analyze the bulk property. I'll come to that in a second. Okay, so so we can actually prove that it's as rich for the 2-dimensional cases as rich as all triangulations of a point set. So 3D gives rise to 3D operations, which I just showed you. Yeah, I think I need to go a little bit faster here. So, and then, this creation of these random things that requires one more operation besides flips, because now you get these kind of weird things here, which is not a balanced point. I think Varda might have talked about it yesterday. We sort of have an operation to prevent this type of everything lying on one side of a plane, because then can't handle stresses of the same type. So for example, the same type means same sign. Suppose you have like packed spheres or something, the only kind of stress they can handle is compressive stress. They cannot handle tensile stress. So that means that you can't have things all the members on the same side of a line, because then you can't have all the stresses of the same sign. So to prevent that, we have some adjustment operations, which we call balancing. Also has an algorithmic structure to show it converges and things like this. Okay, so so this is showing that, so you can't have things like that. Okay, and then design the operation also, as I said, creates these have a specific way by which if someone says create a cylindrical hole, spherical hole, and so on and so forth, we can do that using these flips. As you can see, if you interpret the corner sharing tetrahedra as incidences between fibers, the corresponding irregularities is the regular kind of structure, and corresponding irregularities give you something that looks, we think, a lot like these fibers, which is this carbonated fibers that I used for the heat shields in NASA. Okay, so and one of the, as I said, we have made a list of design operations. The first one was boundary stiffening. The second one was adding irregularities and having a space that you can explore and formalize stochastically. And then this is a third operation, which is refinement, which, it's important because all of these are multi-scale materials, hierarchical materials. So here shows a corner sharing tetrahedra where one of the tetrahedra has been refined into another set of corner sharing tetrahedra. And this is just showing the same picture in 2 dimensions. There are multiple ways in which you can do this refinement, and this is showing 2 different ways, and you can mix and match. So at the next stage, you can perform a different one and so forth. And again, this gives you a martingale-like random, I mean, if you add irregularities along the way, using those flips, you get this whole rich space of possible structures that you can create, and you have control over in terms of rigidity, in terms of how to analyze the random structure, and generative model that you can generate this irregular structure in locally, so that you don't have to remember the whole thing for printing and so forth. So again, refinement, we have a couple of ways in which we can refine. Is the obvious way, in which you simply refine each tetrahedron here. And then there is another way, which I was showing here. The corresponding three-dimensional version also exists. Okay. Next operation is to be able to, because of standard methods in which shapes, larger shapes are decomposed into smaller tetrahedralized, so to speak, and then each tetrahedron is filled with microstructure, and then they're all glued together. The gluing is joining or gluing of these potentially irregular microstructures is also an important thing, while maintaining, again, rigidity and other properties. So this is actually showing that. Then the other final thing is to be able to combine it with some continuous representation. And so there are two different sort of operations that we allow. One is to take the entire cost domain, which is just a usual regular tetrahedron, and to sort of curve the whole domain. So that's one of them. And the other one is to attach to the individual tetrahedra or individual triangles of the layers, sort of splines to the members. So those are and again, in that, there are two different parametric and, implicit spline representations. So there's this type of a map of the whole domain, and then there's an attachment of spline. So we have used both of those to create structures that look like that. So, yeah, so and then the last one, in fact, I mixed the two together. This is the last operation. This is E, and this is F, which is the overall what they call free form deformation, which takes your domain, which always looks like this, the regular version, and then you curve it and so forth. So, so essentially, and as I said, we already did the gluing. So we created this type of a structure. We can model these type of structures by combination of all of those operations, free form deformations, flips, refinements, boundary stiffening, all of them have been used to do this. And of course, there's, our common, the Maxwell counting, which can actually be, which was used to provide this ability to stiffen the boundary for arbitrarily large costs. As I said, it's a very special structure for which, even though 3D rigidity usually is not, it's a hard problem, we can do this. The other thing that this is basically also talking about the interoperability with the sort of a standard technique that people have is to think about these objects as made up of layers. So because our costs automatically have these four sets of parallel layer structure, we can use these methods for solving PDEs and stuff that are based on foliations also. And we can, in fact, think about many of the operations that I talked about, gluing and so forth, in a layer by layer basis. And it helps us, and because you can think about it in the layer by layer basis, these foliation based methods, which, split up the domain appropriately based on the particular physics PDE constraints that they have. So it's called isogeometry. There's a technique called isogeometric analysis, and that sort of splits up the domain appropriately to the particular PDE that they're trying to solve. And so essentially this foliation method is used for that. And the fact that our microstructures have this layered interpretation is useful for that as well. So I already mentioned this, that you can think of it as many physical interpretations, but this is just sort of recapping those. So finally, as I said, we can use a discrete analysis of the of the various properties, mechanical, electrostatic, whatever, and do it really quickly by just using the discrete representation directly. And we did some of that, both directly using the discrete representation for computing stresses and connecting that with the representative volume element to use the discrete method to sort of figure out what the representative volume should be. Representative volume is the size of this irregular microstructure that can be this minimum size of the irregular minimum volume of the irregular microstructure that can then be treated as homogeneous, right? So computation of the representative volume, in fact, requires solving some kind of a PDE, often using these Apollonian packings they use for concrete and things like that. And I attempted to do this using the discrete representation directly, and then you can connect it to whatever finite element or whatever continuum representation solver you have. So so this is just your the usual rigidity matrix. We all know how to compute the stresses. If you have a force, you have a force vector, you have F plus omega R should be equal to 0. Force is the force per unit length edge. Here's the rigidity matrix. So if you have an external force, that's on a simple thing like this, this is what it would look like. The tensions are shown here, the compressions are shown here, and here there's almost no stress. So the same thing for a tetrahedral object, and this is a picture that I already showed before. Very quick, immediate, almost analysis because just a simple linear system. And there's a guy at the manufacturing demonstration facility or something like that. His name is Poon Kim. It's in ORNL. It's attached to ORNL, and he was very interested in our discrete method, and he did a finite element calculation for the same object. Hopefully that's the next slide. Yes. So this was their finite element calculation, taking the same object and thinking of it as continuous bars or whatever it is and doing this. And this was our instantaneous rigidity based calculation. And he was quite, we did an actual comparison. Of course, this is uniform on every bar. This actually changes along the bar because they're taking each of these as continuum and doing it. Another such comparison using another sort of static determinate structures, discrete method that they use, which structural engineers use, not mechanical engineers. It's called truss method, and even compared to the truss method, ours ran like half the time. And of course, the results are almost exactly identical. So we can use, as I said, use the discrete method to then compute representative volume for continuum mechanics computation. So in other words, it's interoperable with that. And so, and the attachment of these continuous splines and so forth on top of the discrete structure allows you to then, do your PDE analysis. So essentially this was heat propagation for the helmet type thing, which is filled up with our microstructure. Heat equation is one of the easiest ones to do. This is, as I said, one of the standard ways is this isogeometric representations, and where you have these foliations, and then inside that itself has these continuous splines attached to the discrete members. These splines allow you to do the heat equation computation along these, how it propagates along these bars, and that was done. This is my co-author stuff. So solving collocation, different types of PDAs, Can-Hillard, Navier-Stokes, and so forth. Because of these splines that are attached to these members, you can apply all of that directly. We also did an electrostatic calculation for, as I said, if you analyze it, the electrostatics and mechanostatics, what we know as stresses are very similar. So using that, we were able to solve something about a capacitor, optimizing the structure of the capacitor, the dielectric constant of the capacitor, how it should be distributed so that you don't have, so that there's no breakdown, so that the maximum stress is, electrical stress is minimized. So we did these problems, and the last thing is printing. So we because we have this method of generating irregularities and in a generative manner, so we were able to generate this huge microstructure on the fly, essentially, and create these slices really quickly, particularly because it's a discrete representation. Oh, excuse me, I don't know what's going on. Okay, seems to have stopped. Okay. So this is actually a movie. I don't know if it'll work. We'll see. Maybe I should just click here. There we go. Whoops. Can you see the movie?
It hasn't started yet, but we can see where it's going to start.
So it's all done in real time, essentially. It's printing, so to speak, in real time. And you can change the slice plane whichever way you want. It doesn't make any difference. Okay, so that's that. Where is it? Okay. And this was another similar. This is a little more about how this slicing is done, especially because we have irregularities, curved microstructures, and so forth. I mean, you can imagine slicing the way I showed it directly on the domain, which is a totally regular cost. It's easy to do, but then if you have, oh, wait, we don't want that. Why is it not stopping? Okay. Okay, so let me go back to present. Okay, so you have this first of all, there's irregularity. Second of all, you're curving it. You have this overall freeform deformation. So when you're going to slice, the slice looks quite bad. It's not the same as slicing through something that's regular. You're slicing through something that's curved and so forth. So it requires some work. And so we've just written a small paper about it, and hopefully we'll be able to present it. If I get a chance, I'll show you another picture from that new paper. It's on archive already. This is something we actually printed. So we printed this corner sharing thing. You can't see it's not boundary stiffened, but you can't see the irregularities. There are irregularities in here. Okay, so one of the problems is we have, for which, as I said, there was a small overlap with the NSF FRG project, in which we were doing realizations of distance constraint systems. And that problem comes up here when we do the gluing, because we are essentially we're changing certain distances. And when we glue things together, we quote unquote change distances, which we can't do, for example, if we are trying to think of the corner sharing tetrahedra as packed particles, then you can't suddenly change the distance. So in other words, you have to then put the distance back to what it had to be and then resolve the system. So realization is something that comes up, for which we used a technique that we have used in the past for multiple things. This is the scale parameterization technique. And I'm just going to go really quickly through it. And I showed this in my other talk in the rigidity workshop, where we use this technique to solve these large isostatic systems to given distance constraints to find the new realizations. So this is an underlying thing within the gluing operation that I talked about, which is, I think, operation 2. So, and this, it was very nice to have techniques that I was using, very basic mathematical algorithms to be used within this very applied setting of designing microstructures. So anyway, there was various different things that the rest of the slides are just showing that there are different things that I had worked on purely abstractly in a way, and written mathematical software for, which I could then use towards the various design operations in this project. I think that's more or less takes us to the end. I won't get to this. This is more of an analysis of flips. Hopefully I maybe talk about it at some other time. That's the end of my talk. I'll take answers. I'll take questions at this stage. This is like a discrete analysis of crack propagation.